So at the very end of the last lecture, we kind of wrap up with the concentration inequality of independent random variables, and we start talking about the concentration of random variables with under weaker condition that is no longer just that is no longer independent but satisfies so-called like Martingale difference condition. So just to recap, we kind of like informally say it's Martingale difference thing. Informal condition, we say this is Martingale is we look at the summation of some random variables. Okay, let's say we look at Xi I, summation from I to n. And so it's Martingale because each Xi I is no longer ID. ID is what we have been working on like for the last lecture. But the Martingale difference no longer require they are independent. It only require you to have some condition, expectation of Xi I, condition on all the thing happened in the past, where we say a lot of things happen in the past, including like Xi I minus 1, till Xi 1. Okay, so you can informally understand this past as like all the randomness happened in the past, and we're saying this is equal to 0. In this case, we call this Xi I Martingale difference sequence. And in the last lecture, we kind of like already sees the example where we have this probability matrix, Xi2, Xi1, and the -1, 1, -1, 0, 1, 0.5, 0, 0.5, 0, 1, 0. And this is the conditional probability of Xi2 condition on Xi1. So in the last lecture, we already verified. So in this case, first, Xi2 is definitely not independent of Xi1 because the table does not factorize. But on the other hand, you have Xi2 condition on Xi1 equal to 1, that is equal to 0. And expectation of Xi2 condition on Xi1 equal to 0, this is also equal to 0. Sorry, -1. This is also equal to 0. So this essentially says this Xi1, Xi2 are not independent. But are Martingale difference sequence. But it's a Martingale difference sequence. And finally, we say the Martingale difference would also exhibit the concentration phenomena because the summation of the Martingale difference, essentially the Martingale would also has the concentration phenomena because if we just plot the summation Xi I over time, like this is I equal to 1, I equal to 2, and we kind of like sum them together. This I summation from I to n, this is n. And we see the first step, we're doing some random work, and the second step, we're also doing some random work, and like eventually it's something like this. And the only difference here is, for example, if I have another realization, is something like here. So those two are two different realizations of the random work. And the Martingale difference sequence essentially says they are no longer independent. So for this trajectory and this trajectory, this Xi t plus 1, the distribution can be different. For example, this distribution is like this, 1/2, 1/2, and this distribution is like this with probability 1 equal to 0. But the important thing is the conditional expectation, that is conditional on all things happens in the past, and the single step in the future has an expectation that is equal to 0. So in this case, you will also expect a lot of cancellation happens, and eventually the summation will grow like something like square root n. Okay, so this is last time where we finished. We talked about this high-level picture about what is this Martingale happening. I think today we will be more formally talking about mathematically how we're going to define everything. I think to understand intuition, really you should understand is the major difference is we are no longer independent. What we're seeing is we require weaker condition, that is a condition on the past. The one-step future has a conditional expectation equal to 0. Okay. This is a key idea in the Martingale. So today we'll mathematically define, this is like an informal definition. We never talk about what is the past. So today we'll just be a little bit more rigorous on how we define the Martingale and what is this Martingale concentration inequality. Okay. So this is a little bit like terminology, but you can just intuitively understand. I will talk about intuitive understanding later. So let's say we suppose f1 to fn are filtrations. Filtrations typically can be understood as a set of random events. You can just think of as a collection of a lot of randomness, so that the filtration at I minus 1 time is a subset of filtration at i's time. So you can think we kind of require the randomness to be strictly increased. So for now, you just understand this sigma fi as all the randomness up to time I, from time step 1 to time step I, so that you have this inclusion condition for any I in M. We say this Ci sequence is a Martingale difference sequence. With respect to filtration Fi. I from 1 to n, if the following two condition holds. That is 1, Ci needs to be inside Fi. Okay, this is some condition. We'll explain later what is the filtration and what does this mean. And the second thing is the expectation of Ci condition on the past, whereas which we denoted as a filtration Fi minus 1 is equal to 0 for all I. Okay. So this is the formal mathematical definition. I think everything else is pretty straightforward. The only thing is a little bit opaque if you haven't learned the formal graduate version of stochastic processes. What is the definition of filtration? I think for now, for this class, we don't really necessarily you need a lot of rigorous understanding it. But I think you can just usually understand this filtration as a collection of all the randomness in the past. So we will say the common choice of filtration. Okay, so this is not necessarily always a choice, but we say common choice, or to intuitively understand this, is Fi will be chosen as a sigma field, so-called sigma field of Ci1 to Cn, Ci. So the sigma field, so mathematical definition, this is called a sigma field. But intuitive understanding, you can just say this kind of include all the randomness C1 to I. Just whatever random events can be induced by C1 to Ci, this is included in this path. So this is why like this is like all the past. Okay. So you can think this is just a mathematical definition of like you condition on all the possible paths. That is the sigma field. But I also want to comment if you only choose this filtration to be like sigma field of C1 to Ci, then there's really no need to like write this like filtration notation, and you can just basically just say I condition on all the paths thing. So sometimes in the later lecture, like we might need to use some filtration, slightly different filtration. I think the comments here is like the filtration can add more randomness. To filtration. So in a sense, all we need is we satisfy like those two conditions. So you can actually choose some other type of filtration. For example, you can also, an alternative choice would be if I have not only C, but also like some zeta random variable. So I can also choose this filtration I to be the sigma field of C1, zeta 1, C2, zeta 2, zeta 2, and until Ci, zeta I. So in that case, I still satisfy, like for example, the randomness like strictly increase for this filtration, and also the random variable Ci is is in this filtration Fi. So this is also another valid choice. So sometimes we can include some more randomness into this filtration, and if we can prove the Martingale kind of condition holds, many different condition holds for this like different filtration, and then we also say this is like a Martingale difference. The only difference is like the field filtration definition is slightly different. Essentially, like intuitive understanding is like what do you include in the path? It's not only like just C1 to Ci minus 1. Sometimes you can also include some other random variable, other random events into the past. Okay. So finally, we already defined what is so-called Martingale difference sequence. And then we can define what is so-called Martingale sequence. Okay, so Si, I from 1 to n, is a Martingale sequence. Or a lot of time, you just call it Martingale. If and only if this Si is equal to some summation of Cj j from 1 to I, and this Cj is a Martingale difference sequence. Okay, so essentially what we're saying is summation of the Martingale difference is the Martingale. So we call the sum to be the Martingale, and each individual summand called the Martingale difference sequence. Okay. So this is like a mathematical formalism, but the intuitive understanding is really this informal. It's just filtration is just the past, and all we have is just condition on the past. The conditional expectation is 0. So given the definition, now we kind of like we're ready to state the concentration inequality for Martingale difference sequence. It turns out what are we gonna say here for Martingale difference is basically identical to Hoeffding's and Bernstein inequality. The only difference is precondition. We kind of relax the precondition from requiring all the random variable to be independent to now we only require all the random variable to satisfy the Martingale difference condition. Okay. So the theorem now is called Azuma-Hoeffding. My intuitive understanding is like Hoeffding is originally for independent random variable, and you can have Azuma-Hoeffding, which is basically strengthening it to like a Martingale difference. And later we also have the Azuma-Bernstein, essentially the Bernstein version of Martingale difference. Okay. So the theorem is very simple. It's pretty similar to the Hoeffding's inequality. So we just suppose this Ci, I from 1 to n, is a Martingale difference sequence. With respect to like filtration Fi. And remember for the Hoeffding's inequality, the most important precondition is like the random variable need to be bounded. So here we also essentially assume the same thing. We say for all I, any I in from 1 to n, we have Ci is supported on an interval with length Ri with probability 1. For most cases, we just understand this Ci is bounded. This is fine. And then we have essentially the same concentration inequality. That the probability of this summation, I from 1 to n, Ci, greater or equal to t, is less or equal to minus t squared, e to the minus t squared over 2 times summation I from 1 to n Ri squared. Okay. So that's essentially the same thing. We still have the bounded, bounded random variable is still like our main precondition, and the concentration is the probability of some tail probability that is the summation. And here we no longer subtract the expectation because by assuming this Martingale difference sequence, we essentially already assume like this expectation is equal to 0. So you should think this Ci is something like something roughly like something xi minus exi or something like that. So we already subtract the mean. So that's why like it's corresponding to the Hoeffding's inequality. And the remaining thing is basically the same. We're seeing the tail probability is smaller than something that like exponentially small with respect to t. And you can do essentially the same operation. We say we make this delta and we can like solve the upper bounds for this summation Ci, the Martingale. Okay. And we will not repeat that kind of part. So any question about the theorem statement? Yes.
So this is the difference between this and Hoeffding is that the two move from the top to the bottom. Or,
Is it? No. No. I think probably I may have made a mistake. I think it should be exactly the same. So Hoeffding has a 2 on the top, right? Sorry. Just want to make sure Hoeffding has 2 on the top. Yeah. Let's do that. Thanks for pointing out the typo. Okay. So if no question about the theorem, we will just briefly talk about how we're going to prove this. The most of the proof is like going to follow the same arguments for the Hoeffding's inequality. So in order to do this proof, we need to essentially recall how we proved the original Hoeffding's inequality for independent random variable. We have 3 lemma, and the final theorem is just proved by simple combination of 3 lemma. So the lemma 1 is Markov inequality, which of course we don't need to modify at all. So at that time, lemma 2, this is like a recall the proof of independent, the proof for the original Hoeffding's inequality. The second lemma, we're saying the summation of independent Gaussian. Has good concentration. And the third step, we're seeing bounded random variables is sub-Gaussian. Bounded random variable is sub-Gaussian. So those are 3 lemmas we use to prove the original Hoeffding's inequality. And we can check first the Markov inequality, of course, like we don't need to change anything. So this is like done. We don't need to do any extra work. And then this bounded random variable is sub-Gaussian. This is regarding a single random variable. So this lemma actually has nothing to do with whether it's independent or whether it's like a Martingale difference. All it says is for a single bounded random variable, it is sub-Gaussian. So this one we actually also does not need any modification. We just directly use the same lemma. So the only thing that's going to relate it to whether it's independent or it's a Martingale difference is the second lemma, where we see the summation of independent sub-Gaussian has good concentration. And we essentially need to modify the proof for the second lemma. We need to strengthen the second lemma to move from independent to like the Martingale difference. Okay, so this is like what we will do here. So the new lemma, let's call lemma 2 star. It's a new lemma we're going to prove. We say let's see I from 1 to n, be Martingale difference sequence. where for all lambda in R, we have the following precondition, that is the expectation of the e to the power of lambda Ci. So in a previous definition, it's just this like a moment generating function. We say it's bounded by some exponential. And now the only difference is we essentially need to say this expectation is again a conditional expectation. We condition on whatever happens in the past, that is a filtration of I minus 1. We say this expectation is upper bounded by e to the lambda square sigma I square over 2. Okay. Then for all t greater than 0, greater or equal to 0, we have that the probability of summation I from 1 to n Ci greater or equal to t is less or equal to e to the minus t squared over 2 summation I from 1 to n sigma I squared. So everything is the same as the last lemma. The only difference is now we kind of adding the condition, like change this original like unconditional expectation to now the conditional expectation, because it's no longer independent. It's a Martingale difference sequence. Okay. So let's prove this lemma 2. So we will essentially follow a lot of steps. Like in the last lecture, how we proved the lemma 2. The first step is we kind of like we first write out what we want to prove. That is probability of summation Ci greater or equal to t. The first step, we raise everything to the exponent. So we say this is equal to the probability of e to the lambda summation I from 1 to n Ci greater or equal to e to the lambda t. Okay. This use the fact that lambda is greater than 0, greater or equal to 0. So basically e to the lambda t is like monotonic function with respect to t. And again, we will use Markov inequality. So we say this is less or equal to e to the minus lambda t times the expectation of e to the lambda summation I from 1 to n Ci. This is using the Markov inequality. So let's first recall what do we use in the independent case. Recall in the independent case. So in the independent case, we use a very important equality, that is for anything independent, the expectation of the product of independent random variable is equal to the expectation, the product of expectation of each independent random variable. So we have e of xy equal to ex times ey. So in this case, we can essentially make the second part to be the product of I from 1 to n and the expectation of e to the lambda Ci. Okay. Essentially, we pull the summation to be the product outside the expectation, and then we use the property of independent random rule. We can also pull the product outside the expectation. And then for each expectation, we can just directly use a sub-Gaussian condition, and this finish the proof for independent case. But for now, we can no longer do that. So we kind of realize for martingale difference, the key is essentially we can bound this term now with the relaxed condition, with a weaker condition, weaker precondition. So how are we going to do that? Actually, it's also not that difficult. So what we can do is we again look at the important quantity which we need to bound here. That is expectation of e to the lambda summation I from 1 to n Ci. So what we will do here is we will do the expectation in 2 steps. So we will first take expectation over only the last randomness. So essentially, we will basically condition on n minus 1, condition on the history up to n minus 1 time, and then we essentially only take expectation over the very last randomness. And then we take expectation over the history. Okay. So essentially, you should understand, like intuitively, this understanding is like this expectation is taking over Cn, and this expectation is taking over Cc1 to n minus 1. This is what this equation really means. So the good thing is if we look at the like expectation inside, that is we condition on the past. When we condition on the past, a lot of things on the exponent become deterministic because we kind of condition on the past. So we can move that outside the expectation. So what we are saying is this is expectation outside. And what we can do is we move this e to the lambda summation I from 1 to n minus 1 Ci. Outside this conditional expectation, and inside expectation, we only have expectation of e to the lambda Cn, of conditional expectation of fi minus 1. Okay. The reason is because recall the inside expectation, we only take expectation of Cn. So only Cn is random. Everything else is essentially fixed given the history. So that's why we can move everything else fixed outside the expectation. So inside, we only take an expectation over Cn. Okay. So you already realize why we do this, because now we can use this precondition for the very last step when we replace this I equal to n. So we say this is less or equal to expectation of e to the lambda summation I from 1 to n minus 1 Ci and times e to the lambda square sigma n square over 2. Okay. This essentially just use a precondition. We call like Martingale sub-Gaussian or something. Like it's a bit informal. So by now you will see how it goes. Because we start with this moment generating function that is summation from I to n. Now we end up with this moment generating function, but a summation from I to n minus 1. The only extra thing we get is we times some scalar. Okay, this is scalar. This is not even random. This is just some scalar. So we can essentially repeat the whole process again and again. So we say this is also less or equal to the expectation of, for example, we can move n minus 1 outside. So what we will end up with is summation from I to n minus 2 cos and times e to the lambda square sigma n minus 1 square over 2 and times e to the lambda square sigma n square over 2. So eventually we can repeat the entire process again and again, and we end up with a single scalar that is e to the minus e to the lambda square and summation I from 1 to n sigma I square over 2. So the final step is basically the same. We can just say, we start from the very beginning, where we say probability of this summation greater or equal to t is now less or equal to e to the minus lambda t, and we plug in the results we have for this expectation, that is e to the lambda square summation I from 1 to n sigma I square over 2. And we again, so for optimal lambda and to minimize the right-hand side, and again, this lambda is some quadratic formula on the exponent. So what we can do is we just pick the optimal lambda equal to t over summation sigma I squared. This is exactly the same as the last time when we do the independence of Gaussian. And this becomes less or equal to e to the minus t squared over 2 summation I from 1 to n sigma I squared. Yes.
So the 2 does end up in the bottom?
So the 2 ends up in the bottom. Yes, and this is like in the lemma. So in this like lemma about the sub-Gaussian 2 is in the bottom, but in the original Hoeffding bound 2 is on the top because we still need the third step. That bounded random variable is sub-Gaussian. So eventually you need to choose like this sigma equal to r over 2 or something like that.
Wait, so when we're doing lemma 3, we have to get out that conditional expectation instead of just like the normal non-conditional expectation. Does that change lemma 3 at all?
Yeah, so I think this is also a good question. If you're not convinced, it's a good exercise to think about at home. But basically the main idea is in this like Azuma-Hoeffding inequality, we're assuming that no matter what is the past, the Ci is like always bounded. So that bounded random variable is also modified to be like basically conditional on whatever happened in the past is bounded. And then it's just a single, as I said, it's like a single random variable thing. So you can just repeat the same argument and you prove the same thing is true. Okay. So basically everything is the same. Except now we make the condition weaker, and which we will actually leverage this weaker condition in the later when we do the reinforcement learning, because in the reinforcement learning setting, we don't have the luxury to make everything independent. We actually will encounter a lot of cases that is like a martingale. And finally, after introduce the Azuma-Hoeffding, I will just quickly give the result for Azuma-Bernstein. I will no longer do the discussion because everything is the same as Princeton. The only thing different is like the precondition is slightly weaker. So the Azuma-Bernstein inequality we again suppose we have the martingale difference sequence. With respect to the filtration, that is fi, I from 1 to n. And we have the following two conditions. This is for simplicity, say this Ci is always bounded by R with probability 1. And the variance, I think important part about the Bernstein inequality is the variance of Ci, condition on filtration I minus 1, is bounded by sigma I squared. Then we will have that, again, the probability of summation I from 1 to n Ci greater or equal to t is less or equal to e to the minus t squared over 2 summation I from 1 to n sigma I squared plus 2 over 3 RT for any t greater than 0. This is essentially the same bound. We have the summation of the variance, and R we no longer have the summation, but we have extra t here. And eventually this will be the leading order term, and we can still do the discussion like this leading order term depends on summation of variance, while the previous Hoeffding depends on the summation of the bound. So this will be slightly sharper. So this will be basically everything we want to talk about. Yeah, any questions? No? Okay. Oh, this is basically what we want to talk about for the concentration inequality. So we just want to wrap up and summarize what we have learned. And if you kind of feel you're not very sure about the proof, it's okay. I think in the later class we will never use the proof for concentration inequality. All we need is we need to use the results. So we basically talk about the 4 different inequalities. That is Hoeffding's inequality, and the second one is Bernstein's inequality. Third one is Azuma-Hoeffding. And the fourth one is Azuma-Bernstein. So the Hoeffding is given for independent random variable. Independent. And plus independent and bounded random variable. So the Bernstein is for independent and bounded random variable, but with sharper variance condition. So in this case, when the variance is like much smaller than the bounds, so this will be sharper than the previous one. And finally, we just relax this independence condition from Martingale here. And everything else is the same, like it's a Hoeffding and Princeton, it's correspondingly it's the same. Okay, so for now, I hope you now feel like very powerful. You have been through like already the most difficult mathematical contents of the course, and now like when we do the statistical estimation, we can essentially just call this like concentration inequality, and we already have like pretty sharp like guarantees. And you will do this in homework, and we will also see more in the lecture. So. Before we go to the talk about reinforcement again, I will also talk about another mathematical bounds, like very simple bounds, which but we will also use a lot. It's easy to see it here in isolation. It's very easy to see it. It's called a union bound. So the simple union bound is as easy as the following. That is, let's call it proposition 1. So I'm sure you will learn this from every basic like probability and statistical course. We're saying for any random events, A and B, random events are not like independent, are not random variables, are just events. So we say the probability of A union B is that either A happens or B happens. We notice this is less or equal to PA plus B, PA plus PB. Okay. So it's very intuitive. The probability of either A happens or B happens is less or equal to the probability of A happens plus probability of B happens. In fact, we can see the right-hand side is equal to the probability of either A or B happens plus the probability of both A and B happens. So this basic form is pretty it's very straightforward, and I guess you will immediately see it from like writing out the equation. I will write out a slightly transformed form we will use a lot throughout the lecture. I think it's easy to see it here, corollary 1. So this is like immediate corollary of this proposition. And for example, if we have a lot of events, and we know the probability of each individual events happens with high probability. That is, the probability of each individual events AI is greater or equal to 1 minus delta for all I in N. Okay. And then we need to calculate the probability of, so each individual event is happen with high probability. What I want to know, what is the probability of all those high probability events happen simultaneously? That is the union, that is the intersection of I from 1 to n. Okay. So what is this probability? Like all the high probability events happen simultaneously. It turns out you can also prove this probability is greater or equal to 1 minus n delta. So essentially you pay a n factor here. N is the number of events you're taking its intersection over. And this corollary is actually a directly corollary of this like union bounds. We will immediately do some proof here. So later on, we will essentially always like use concentration inequality to prove for some events holds with high probability. And then we want to say all the concentration happen simultaneously, and then we just essentially do intersection over all of them, and we pay some n factor there. And that's usually how we handle the math there. So this corollary why this is true, and we essentially we first write out what we want to bound. And one way to calculate this is we look at the complement of this set. So the complement of the intersect of this AI is actually equal to the probability of union of the complement of AI complement. Okay. So the events of all AI happen simultaneously is the complement of at least one of the AI bars happening. So that is, in order to do a lower bound for this, we only need to do an upper bound for this complement. And we just look at the probability of the union I from 1 to n AI bar. And now we can immediately apply the union bound. This is less or equal to the probability of A1 bar plus A2 bar until like probability of AN bar, which we know each AI bar is upper bounded by delta. So this is upper bounded by n delta. And we finish the proof. Okay, any questions about the concentration inequality union bound or whatever we have talked about so far? And if not, we're gonna move to the next part. We're gonna talk about how we're gonna do the learning for like MDP, reinforcement learning. Okay, so as we promised earlier, all the reason we kind of do this concentration inequality is because we're not only interested in the planning of MDP, but we're also interested in the learning of MDP. So we will start with the easiest learning setting that is called a generative model. Or a lot of literature also call it like a simulator setting. So I still want to recall, it's a bit time, like last week, we always focus on this MDP, where we have a lot of elements. That is the set of states, set of action, reward, transition, and also the horizon. So in the last lecture, we're talking about the planning. That is, we need to know the environment. That is, entire P and R are known. So today we will talk about the learning setting. This PR are not unknown. So whenever we talk about a PR and unknown, we need to talk about how we're going to collect the samples to learn those PR. Like what is the protocol to collect data. So the simulator setting is one of the easier setting, like how we specify the collect data. And later on, we will talk about more challenging, like online and offline setting. So for now, let's focus on the tabular setting. In the tabular setting, we means this state and action are finite. The set has finite cardinality. Okay. And in the second half of the course, we will generalize this tabular to more generic, large state space, or you can have infinite number of states or something. But for now, let's just focus on the simplest case. That is, we have finite number of states and a finite number of actions. Okay. So what is simulator? Simulator, you can, in general, be understood as a black box. You have a simulator here. So simulator is one specific way to collect data. So the simulator will essentially allows you to take some input. So you can ask simulator what is state, what is action, what is current step H. So this is the input of the simulator. And output of the simulator is the S prime, which is the next state. And this is stochastically, randomly draw from the probability, transition probability of SA at each step. And also, we will have the reward, R. This is output. And this R will be just equal to RH SA. You can essentially think you have a computer program called a simulator. You can just query whatever the state action H. It will not directly tell you what is a transition, what is a reward, but instead it will give you a random sample of the next states and the reward. We will comment a little bit here. We will again assume this reward is deterministic. That it has no randomness here. I think the reason it's okay in a sense, it's not with it's without loss of generality, because in this case we usually need to learn two things. That is this S distribution, where this is multinomial distribution. And the other thing we need to learn is the reward. And in fact, we only need to learn the mean of the reward. That is expectation of reward. And we assume it's deterministic is okay because in general, learning a multinomial distribution, is harder than learning the expectation of a scalar random variable. So it turns out, I think, although we assume it's deterministic, but if you make it random, like all the proof will be easily translated there with very little modification. So it's for simplicity, we just assume reward is deterministic, and only the randomness is through the next states, the state generation. So let's intuitively understand what is this power of simulator and what it tells us. Let's look at an example of like a maze. Okay, maze essentially is a map where you have a lot of walls here and there or something, and okay, let's just randomly draw something like that. And we have a starting point here. And we have an end point here. Let's call it start. So in this problem, we can formulate as an MDP, where state is like the position in the maze. And action is essentially we have 4 possible actions. We can move upwards, downwards, and move leftwards, rightwards. Essentially, we have 4 actions. So the next state, the output of the simulator, or usually the next state, is the position after moved. So in this case, for example, you are moving towards the direction of war. Like, for example, you are moving on the right, like you're going right. You're taking an action to go right. And in this case, you are stuck in this position because you cannot go right. But if you go down from this position, and you can go down. So the next states will actually be a function of the action you're taking and your starting position, and also whether you have a war, like some environment there. So it's like some complicated transition probability. And the reward is essentially you get 1 if you leave the if you reach the end. So we talk about the important thing here is like how we're going to collect the data to learn this maze. Like imagine you are an agent. So you actually you don't really know the map of maze. So you cannot really know whether you can go right at this position or not. You're keeping the duck. So in this case, I think the simulator setting is essentially corresponds to the way of learning. Essentially, you can query any state action pair, and you get a next state and reward. So essentially corresponds to agent is allowed to teleport to any location to learn the map in the neighborhood. In this case, like in the maze problem, like the entire environment is essentially the map Okay, and the query of any state action pair kind of corresponds to you are allowed to like teleport to anywhere. So this is somehow quite strong, and for some application, for example, for some simple games, you're actually able to do that. But for a lot of complicated games or like for robotic tests, maybe you cannot do something like that. So this corresponds to later we will talk about two settings, online setting and offline setting. And in the later online setting, you are no longer allowed to be teleport to any location. You have to reset to the start location. So this is more challenging because you can no longer teleport to any location. Every time you want to reset, you have to go from the very beginning. So in that case, like if you're allowed to teleport, like scanning through the map is like pretty trivial. You just query all the possible states. But in this online case, even reach some states is not very trivial. Okay, you need to have some reasonable policy so that you can reach some location of the states. And in the offline setting, you're given some data, given some trajectories collected by other agents. So in this way, it's also more difficult in a sense, like now in a simulator case, you're allowed to teleport to any location. You want to learn whatever. You can basically learn whatever you want to learn. But here, you're kind of like very limited to what other agents have done so far. And you need to learn good policy from those limited data collected by other agents. So those are two more challenging settings we will talk later in this lecture. So far, we will focus on the simulator for now, because this is an easier setting, and we will always start from the easier setting and do the result there first, and then we go to the more complicated scenario. So we just want to recall that the final goal of reinforcement learning is we want to find some policy let's say pi hat, so that I think a lot of times, because now we have the statistical arrow, like we're never able to find exactly the optimal policy, but we want to find something close to an optimal policy, like we say epsilon optimal. And epsilon optimal is measured in terms of a value. So we will look at the value of the initial states. Let's consider, again, the fixed initial states. So basically, this is the optimal value we can achieve. That is the value achieved by the optimal policy. So in terms of epsilon optimality, we need to measure the value in terms of the comparison to the optimal value we can achieve. So a typical way is we say this subtract the value of the policy we find by the algorithm is upper bounded by epsilon. So in this case, we're guarantee our value is like reasonably large. Is at least the optimal value subtract by epsilon. Oh, because we always have statistical arrow there, right? We only observe the sample. And even with concentration inequality, we have some error in estimating the true probability. We're never able to learn what is true probability. So you always suffer some statistical error. Okay. And one of the very important questions we will ask in this scenario is also called sample complexity. So sample complexity, essentially, we will ask like how many queries we need. Query, essentially, we say, one query is like we ask simulator one SAH, and the simulator give me one next states and one reward, because we call it one query. And we say how many queries we need to find the epsilon optimal policy. Okay, so we're already talking about the setting. Now let's talk about our solutions. If you're given this simulator setting, what would be the algorithm you're going to develop to solve this? We say so in the planning scenario, we give exactly the P and R, and then we can directly use the Bellman-Optimality equation. And now the only thing different is we no longer have access to the P. So one naive strategy you might think of is I want to first use this sample to estimate P, and then I would just directly use the Bellman-Optimality equation. And that sounds like a pretty straightforward solution. And this is exactly what we're going to study next. So we essentially so the only thing unknown here is the transition probability. The reward is more or less deterministic, so we don't really need to estimate it. So one way to estimate this transition probability of PHSA is we can calculate the empirical frequency. That is, we will essentially sample a lot of S1 prime, S2 prime, till Sn prime. So we'll sample a lot of samples by query simulator. The same SAH. So we'll basically keep repeating query the simulator, the same step H and the same state action SA. And then we get a lot of the next state samples. They're all random samples from the next state distribution. And we will estimate this transition probability to be basically the empirical frequency. That is 1 over n times the summation I from 1 to n indicator of Si prime equal to S prime. So what is the probability I'm going to estimate? I will just look at all those samples, and I see basically how many times I observe the next state is exactly equal to S prime. And I divide it by n. This is essentially my empirical frequency, and I use this as my estimate of the transition probability. So this gives a very straightforward algorithm we're going to actually analysis. That is, again, we call it value iteration, but in a simulator setting. We're essentially just doing this 2 steps. We first estimate the P, and then we use the Bellman-Optimality equation. So user need to specify what is this n sample here, how many samples we need to collect for each state action pair. And then the algorithm will run the follows. That is, for all state action H, essentially we do a sweep over all the state action pair and for every step. We do the following, that we will query SAH, and collect n samples. That is S1 prime till Sn prime. And I will directly do the estimation of the transition probability. By this star equation. Let's call this a star. All S prime in S. And then we will just do the Bellman optimality equation. Let's compute. The only difference to the original Bellman optimality equation is now we no longer have access to the P, so we will use the P hat, our estimate, to replace P in the Bellman optimality equation. VH star hat SA is equal to the max taking over action Q hat star SA. And the output is just a greedy policy with respect to this Q hat, which is we output this pi hat H S is equal to just the argmax A over Q hat H SA. So essentially it has two steps. One is you estimate the transition matrix P. And the second is doing like a value iteration, original value iteration, that is Bellman optimality equation, on the estimated MDP, which use the new transition P hat, our estimate, and the reward. Essentially, the algorithm is following these two steps. Okay. This is also like what we will think. Yes.
This is assuming that we know R for sure, but this is just the...
Right. I think because we're going to take a sweep over all the state action pair, and so you're all going to observe the reward at least once. And because we assume it's deterministic, so we kind of just know the reward. So I didn't write it here, but you should like just collect the reward. Okay. So one very important thing here we want to still know, like in terms of theory, is like we said about sample complexity. Like we just say we're going to collect n samples and do this estimate. But the question is how many samples we need to collect so to guarantee we're going to have the epsilon optimal policy. And this is what we're going to address in the next lecture. We're going to compute, essentially provide some guarantees for the sample complexity of this value iteration algorithm. And we will actually see like roughly how many samples we need to learn to we need to learn an MDP, like learn the optimal policy accurately. Okay, and how it scale with number of states, number of action, and the horizon length.